Okay, so we're going to start with this recap problem. In the gambler's problem, true or false, in the gambler's problem, the gambler gets a reward whenever they win a bet. Let us see what you guys said. Let me try to zoom out a bit here. Okay. You guys said 9 people said false, 4 people said true. Very good. The correct answer is false. False. Common misconception, you think you go to the casino, I won the bet, I get rewarded, right? But remember, reward has a special meaning in this course, right? It's the rewards in the process, and in the gambler's problem, they only get a reward at the end, right? If they win all the way at the end, they win. Similarly, in lab number 2 that you guys handed in, that gambler's problem, you don't get a reward if you just win a bet, right? So you bet $1, you go up, you gain some value. You certainly gain some value because you're in a more valuable position. Having a bankroll of X plus $1 is more valuable than having a bankroll of X dollars. So you have gone up in sort of net worth, but you haven't gotten what we're calling in this course a reward. So that's important to remember. The reason I'm telling you this is because in lab 2, lots of people got the code completely correct and did great on that. The explanations for what are the Markov decision processes, a lot of people got wrong. So a lot of people made mistakes like this. They said, what are the rewards? They said, oh, every time you win a bet, you get a reward. In the first problem and in the second problem, a lot of people missed that the state space is a product of 2 things, right? So the state space is not just how much money you have. It's how much money you have times, like Cartesian product, how many rounds are left, things like that. So I will be handing that back soon. It's 99% marked, and a lot of people made mistakes on that. So just watch out for that. The other really big issue is almost nobody mentioned in problem 1 the fact that there's turns, right? The player takes a turn, the dealer takes a turn. Almost nobody mentioned that. So make sure you go watch the solutions video, which is posted on CourseLink if you were confused about that. There's also lots of people who got it completely correct, and their code was fine. Like I gave them full marks on the code. You do have some tips and tricks you can learn if you want to improve your Python skills. Go watch the solution video. There's a command called np.indices. So if you want to get good at NumPy, that will help you write code with less loops and kind of more readable. So go check that out if you want to learn more NumPy. So I will hand that out soon. I'm happy to answer questions about the grading or anything once that goes back, probably by the end of today. Any other questions or comments about the lab? Okay, so we're going to go back to what we were doing last time was bandit problems. So we're going to go back to bandit problems, and I will give you a little refresher of where we were, which was this thing. So we had, remember, we were at the lakes. We were deciding which lake should we go fishing at, right? We were the fishing man. Let me go all the way back to the fishing man. We were the fishing man choosing A, B, C, or D. And then we talked about why this is important in real life, including in our problems of deciding which actions to try. And then we got to some definitions for this multi-armed bandit problem. We defined these things. Capital L was the number of arms or lakes. Capital T was the number of days or rounds that you play. And then we had these amounts of regret. So each arm has some amount of regret that we call delta A. That is sort of the amount of regret you get by playing that arm. If you play the best arm, you get 0 regret. You're like, yeah, I played it. No regrets. That's where that expression comes from. When delta is 0, no regrets. Otherwise, if you play a suboptimal arm, you have some amount of regret. And then we defined this total regret, which was this amount, the total amount of regret, and we said that you can rewrite it in this way. Let's go to this slide in full. Enter full screen. So the amount of regret is the sum over all the regrets you have, but you can write it in a nice way as summing over the number of times you played each arm times the amount of regret that arm has, right? So if you play one arm a lot, and it turns out that had a lot of regret, you're going to have a lot of regret. And we want to take the expected value over our strategy. So maybe our strategy is going to change depending on what we see. So our strategy will play different arms different amounts of times. You guys had firsthand experience with that, building a strategy. And in this class, we're going to calculate the expected regret and try to find strategies that have low expected regret. That's what we're going to try to do. And to start with, I have 2 very simple strategies that I want you guys to work on and try to do it yourself. So this is the formula which you will need. And here are the 2 strategies I have given you guys. They're both very simple strategies, and they were suggested last round. So here is the formula again in Mathmatize if you need it. So there's 2 strategies. One is, at the beginning of the game, just choose an arm randomly and always play that arm. Okay? So So this is like the coin flip strategy. Like, I'm feeling lucky about Lake A. Let's go to Lake A for the whole fishing trip. Okay? And I want you to calculate the expected total regret of this strategy. Similarly, I have a different strategy, which is that every single time you pick a new one at random. So at every time t, you just completely choose a different arm, and you play that arm. What is the expected total regret? So these are kind of silly strategies that don't take into account the information you're getting, but nevertheless, it's instructive to see what the answer is here. And when I ask you to calculate the total regret, I want it as a function of t. So there's going to be some constants. It's going to involve L and deltas, but I just want to know, how does it depend on t? Is it growing linearly in t? Is it growing like a square function, a square root function? What is the dependence on the total length? So I'll set you free. Try to remember the problem. Try to see if you can make sense of this formula. How many times will you play each arm with these strategies? Try to figure that out. So I'll give you a few minutes to work on that. Feel free to chat with your neighbors or put your hand up and ask for help if you want some hints. And we'll reconvene in, say, a few minutes.
The number of times you played arm A of the times you.
Okay, yes, and then delta A is.
We use start when I see it up.
Yeah. So we'll see what the options are. It is linear, I think, because it's just it's that delta A constant. But then the second one you're going to be picking. So the expected. It's randomly here, you choose each one over L times. Or rather T over L.
Yeah, there's like 30 seconds left, but who would like more time? Anyone for more time? No. Okay. Maybe you guys all know the answer here. Maybe you have no idea where to start, and more time won't help. Okay, we'll see. I guess in a second, and we'll go over it either way. Okay, let's check out what you guys think. How long will it take? Lots of people are saying if you pick an arm, the total regret you're going to get is some constant c times the amount of time left. Almost everybody is in that one. That's if you pick an arm. I guess this is the first one. If you pick an arm ahead of time and always play that arm. What happens if you do this one? I guess this should say 2, but it says 1 again. At each time you choose a new arm and play that, and you guys think it says... Okay, this one people are a little bit more split. A little bit more split. So about half the people are in c times t still, and about half the people have switched to something else. I will reveal to you that you guys have the right answer in part 1. So in part 1, 13 people said c times t. The right answer is c times t. Does someone have a simple explanation of why it's c times t, or how you went about calculating it? Yeah.
Because no matter what arm you pick, you will have the same delta, and that same delta will be applying to the regret every time. So.
Okay, great. So I see. So you're saying, okay, I guess you did something like this. You're saying if you pick arm A, so this is the strategy number 1. Strategy number 1, which is to choose an arm, play forever. Okay, and if you pick arm A, then each round you get delta A regret. Okay? And you're going to play that arm forever. So what is the total amount of regret you get? You get t times delta A. So when you pick arm A, you get t times delta A regret. No matter which arm you pick, you always get some constant, delta A. Maybe I should write it the other way. Let's write it delta A times A. So no matter which arm you pick, you get delta A times t, and delta A times t is always a constant times t. I guess one thing you have to worry about with these constants is if the constant is 0, the function 0 times t is not really linear in t. So writing it as c times t, we usually mean a non-zero constant. And actually, if you get lucky and you pick the right arm, you will get 0 times t. If you got lucky and you did pick the best arm, there is a chance that you get 0 regret, which is great. So that's totally true. Very nice. Great argument. You see the c times t. Did anybody calculate the expected total regret? So the expected value of the total regret. This is the total. We calculated the total regret for picking arm A, and it's always linear. But what's the expected total regret? Did anybody do that one? This would be another way to see it. This is for each arm, and the expected total regret is sort of aggregating, on average, aggregating all the different arms you could pick. Did anyone try that one? Yeah.
The expected number of times that you pick arm A would be t.
The expected number of times you pick arm A would be t.
Because you pick it every...
Yeah, okay, great. So
okay, that's only for one arm.
that's so if you pick arm A, then you play it t times.
Yeah.
So it's not true that the expected number of times you play it is because you might have picked a different arm.
Right.
But what's the chance you pick arm A? This is the ingredient we're missing. Let's write this one down first. So if you pick arm A, something happens. Let's first go back and calculate what is the probability to pick arm A. What is the probability to pick arm A at the beginning? Yeah.
1 over L?
It's 1 over L. Yeah, we pick all the arms equally likely in this strategy. So now you know if you pick arm A, you get this much regret. You know the probability to pick arm A. And now you can combine them to get the total expected value. So maybe we should have done this one first. The total regret. We add up over all the possibilities, and we add them up. So the sum over all the arms A goes from 1 to L. The probability to pick arm A is 1 over L, and the regret you get is delta A times T, which now you can factor the T out. So it's T, 1 over L. The sum of A equals 1 to L of delta A. That thing in brackets you can kind of think of as the average regret of an arm, right? Each arm has delta 1, delta 2, delta 3 regret. If you add them up and divide by L, that's literally taking the average of all the regrets. So you get the average regret of all the arms multiplied by T because you played T times. That's the perfectly correct answer for strategy 1. Any questions or comments about that? All right. Now what I want you guys to do, my favorite thing in the world. Let's revote. I want you guys to do strategy 2 again and revote, okay? So try strategy 2. You know the logic now. You know the rules of the game. Maybe are a little more familiar. And I hope we can get a consensus on this thing, which is mislabeled as 1, but strategy 2. So in strategy 2, you don't pick an arm at the beginning. You pick a new random arm every time. And I want you to figure out what the expected value is. Okay, I'm going to revote it and give you a few more minutes. Again, feel free to discuss, or if you have a question, please put your hand up and I'll come over and help you out. Okay, we're going to revote. Okay, of course you know the answer to number 1 already, but number 2 is the one we're working on.
randomly choose a new. Including, that includes the one you're on.
Yeah, you were asking if you can play the same arm like twice in a row? Yes. So the new arm might be equal to the old arm with some probability.
Then I don't see this changes. It's just a defect that you would constantly change, right?
Here's a different one that uses the, wait, yeah, I think we use this one.
Okay, there's like 20 seconds left. Put in your guesses if you haven't answered yet. I think most people are in already, but not everybody. Okay, let's take a look at what people said. Show me the counts. Okay, hopefully everybody got question 1. Maybe not, okay. Question 2. So 9 people out of 13 said c times t. 3 people said c times square root of t. The correct answer is C times T. So if you stuck with C times T, you got it right. I guess, how's that 92%? Okay, maybe I'm just bad at arithmetic. Okay, let's not do fractions in our head. It is C times T again. Did anybody calculate what the constant C is? Did anyone do it? Or have an argument of what it should be? Yeah.
Would it just be the same as before?
It's exactly the same as before. And the reason is the expected number of times you play each arm is exactly the same as it was before. So in strategy number two, and again, we can compute directly the expected value of the number of times you play some arm A up to time T. Well, you can either play it on the first round or the second round or the third round. So this is the expected value of the sum from T equals 1 to T of the indicator play arm A at time T. And that is 1 over L. So it's the expected value. I guess I got to switch the order here. So now I switch the order. T equals 1 to T of this expected value. So that's the probability you play arm A at time T, which is 1 over L. So you're adding up 1 over L every time you get T over L. So each arm gets played T over L times on average. So what is the total regret? T over L, but when you play arm A, you get regret delta A, so you get the same answer at the end. So both strategies, even though they look quite different on the face of it, in one of them, one person is just playing one arm every single time, and the other one, they're switching all the time. You get the same total regret at the end. And I want to point out, it is linear in T. Okay, these are like the most basic strategies, and we got to come up with something that does much better than this. This is like silly land, easy strategy. You don't even look at what rewards you got from pulling the arms, and you can come up with a strategy. So we want to do something that's substantially better than this. Okay, here is the one the textbook shows many times, and it is called the epsilon-Greedy strategy. You might have seen it in the textbook or somewhere else, the epsilon-Greedy strategy. Okay, here's the epsilon-Greedy strategy. Actually, before we do the epsilon-Greedy strategy, let's just do just the greedy strategy and calculate the regret of this strategy. Or do I want to tell you epsilon-Greedy first? Let me tell you epsilon-Greedy first. Okay, let's go back. I'll tell you epsilon-Greedy first. So what is the epsilon-Greedy strategy? It is you play the best arm you've seen so far. That's greedy. And we saw that if you play the greedy strategy, you won't not have a great outcome because you can sort of get locked into something that is not the best, right? So if you are always playing the greedy strategy, this will not be great because there's a chance you'll get locked into a suboptimal arm and you won't get the right thing. So actually, if you just do greedy, it is very similar to strategy 1. In strategy 1, you choose an arm and play it forever. In the purely greedy strategy, it's not that you're choosing an arm completely at random, but there is some chance you end up at a random arm, right? If that arm, just by chance, happens to have a high value near the beginning of the game, you will get locked into that arm and you will play it forever. So the greedy strategy has also this kind of behavior of growing linearly in T. So the greedy strategy is actually quite similar to strategy number 1. That is why we need the epsilon. So the epsilon greedy is we're not going to always do this. We're going to do this with probability 1 minus epsilon. Probability 1 minus epsilon. So what that means is every time we play, we will, instead of being purely greedy, we're going to flip a coin that has chance of heads, 1 minus epsilon, and chance of tails epsilon, where epsilon is some small number. So we're going to fix some small epsilon in 0, 1. And so sometimes, or most of the time even, we're going to play the best arm we've seen so far. But on the off chance, we're going to do something that seems silly. With probability epsilon, we will play a random arm. Play a random arm. Or should you say like purely random. Okay. So this is like strategy 2, the second strategy you saw, of playing arms purely at random. And you saw that strategy 2 on its own was kind of silly, like it doesn't do well. Strategy 1 on its own doesn't do well, like just picking an arm and always playing it. which is similar to the greedy strategy. So each of these strategies on their own are not great. But when you mix them like this, with an epsilon, you get a much better strategy. And the reason is, because of this exploration part, this is like an explore part, explore bit. Because of this exploring, you will get a better and better understanding of what is the best arm. So over time, if you've tried every arm enough times, and you'll try them, an epsilon fraction of the total time. So in t rounds, you'll play, on average, you'll do epsilon t rounds of exploring. When you do that, you will have a very good understanding of which is the best arm. So the chances of you getting stuck into an arm that is suboptimal over here, it will go down to 0. And so the hope is that the number of times you play arm A up to time t will not grow if delta A is bigger than 0. So arms that have some regret, you will only play them a few times, maybe not too many times, because of the explore rounds. Okay, that's the hope. And if that is true, if hope is true, what is the total regret? The total regret is going to be the expected value of the total regret. So we're hoping that as t gets very large, the only arm will eventually settle down on, and the best arm will be the true best arm. That will have a regret of 0. So we're going to get sort of the sum from t equals 1 to t of the regret at time t. I'm going to write this like this. The expected value of the regret at time t. And this is all kind of heuristic right now. And the regret at time t, when t is very large, we're going to hope that it is close to 0. And so I'm going to write it this way. I'm going to write the first t equals 1 to large value. That'll be the first number of rounds. So for a long time, we're kind of stuck. We don't know what's going on. We're going to have the sum from t equals 1 to some large value. And we're just going to say that the regret will be 1. We'll just eat the regret. We'll say, okay, we're just going to pretend in the first few rounds we're just getting a lot of regret. That's fine. Because after that, after this value, we will have explored enough that we know the best arm. T equals large value plus 1 to infinity, not to infinity, to capital T. And now we're going to hope that once we've reached this large value, because of the explore rounds, because we've explored so much, that when we choose this thing, I'm going to call this an exploit round. An exploit, right? This whole thing is about the trade-off between explore and exploit. And this is it. We're exploiting here, playing the best arm, and sometimes we explore. So we're hoping that after some number of large rounds, we have fully explored, we know what is the best one, and so when we explore, or when we exploit rather, we're going to get a 1 minus epsilon. This is the chance of exploiting. The chance of exploiting. And then we're going to get a regret of 0. Regret of 0. Okay. And okay, this is all like very hand wavy, wishy-washy. This is like hope, fingers crossed. Okay. So the idea is we're going to explore for a while, then we're going to learn the right value, and then we're going to say the chance of it, when we do this 1 minus epsilon exploit round, we're going to get a regret of 0 because we'll have a good understanding of what is the best one. There is also an epsilon chance of exploring, right? So in our strategy, we play arm at random. And when we do that, that's going to happen with probability epsilon. That will be exactly like strategy 2 that I had you guys revote on, right? So now with probability epsilon, we're playing exactly strategy 2 of choosing an arm at random, and that's going to have the regret, which is 1 over L times the sum of all the regrets times, just like that. A equals 1 to L. So when you play an arm at random, you get this average of the regrets, 1 over L times the sum of the regrets, written in tiny font. Okay, we add this up over T. The nice thing is, because this thing is a 0, then no matter how many times you add it together, you get 0. That's very nice. This t equals 1 to large value, that's going to be some large value. So large value. And then you're going to get plus epsilon times this constant times t. 1 over L times the sum of A equals 1 to L of delta A times t. So if you do the epsilon-greedy strategy, what do you get at the end of the day? Assuming everything works the way you think it does, you're going to get that the total regret is some constant plus linear in t, but the constant is very small. You can make the constant smaller and smaller. You can try to make this epsilon really small to make this thing work. However, it is still linear in t. Still linear in t. Okay. But that's the hope. And so the epsilon-greedy people use a lot. It's a very simple strategy, and this is like vaguely what people think of when they're doing epsilon-greedy. The question is, can we do better than linear in t? Can we find something that is genuinely not linear in t, but is sublinear in t? So in t rounds, can you get less than t regret? That would be an amazing thing. And the answer is yes. And we're going to do a real, actual computation and come up with a strategy that has less than t regret at time t. And you'll see that these are the types of calculations we do. So this one was all very hand-wavy, and we were hoping, but the one we're about to do is going to be rigorous, and it's quite nice. This one is hard to analyze, because it's like, how many times did you play a certain arm up to time t? Well, it's all random because of this epsilon thing. So we're going to do a strategy that is a little bit easier to analyze, but is morally speaking very similar to the epsilon-greedy. Before I show you guys this strategy, are there any questions or comments about anything so far? Yeah.
For the first couple rounds where you haven't explored every arm yet,
Yes.
well, if you just pick one arm first, would that not be the best arm so
Yeah.
far?
So right. So the when we're doing this exploiting thing, that's like pick the best arm. Of course, in the first couple rounds, you have like 0 knowledge. So even though you're exploiting, like you suck. So you're essentially picking at random. And in my little hand-wavy analysis over here, that was included in this first couple rounds over here. So I just like gave up. I was like, in the first couple rounds, up to some large value, like I'm not even going to try, I'm not even going to attempt to like bound away like what you're doing. I'm just going to say you're terrible. You get 1 regret every time, which is the maximum possible regret you can. And that all went into the constant over here.
Okay.
Yeah. So this is a very good point. At the beginning, you don't know anything. And you're exactly thinking of what the strategy is going to be, and you'll see exactly how this comes up. Yeah.
What happens if we anneal the epsilon?
This is a fantastic idea. So do you want to describe what annealing the epsilon means for people who don't know about pottery, I guess?
It decreases over time.
Yeah, that's right. So annealing is a word originally from pottery, where you put you make something out of clay, you put it in the kiln, and the kiln starts out really hot, and then people are like, oh, that'll bake it, and then it'll be really, really hard. But it turns out if you turn the fire off right away, then if it cools too fast, then it'll shatter and break. So you do this thing called annealing, which is like you slowly bring the temperature down over time, and it won't shatter, and it'll have time to harden as it's going down. And this is in computer science. There's this same concept of taking a value that is close to 0, and instead of having it be constant forever and then turning it off, you bring it slowly down to 0. And in this situation, what you can do is instead of making epsilon a constant, you can make the epsilon t strategy. The epsilon t strategy. So what you can do is let's add in let's just write it somewhere else. This is like upgrade. The epsilon t strategy, which is instead of picking one value of epsilon and using it forever, you have a whole sequence of values of epsilon, and they get smaller as you go. So you have an epsilon 1, an epsilon 2, an epsilon 3, all the way up to epsilon capital T. You have this like schedule of epsilons that is going down to 0. That's why it's called annealing. And then what you do is you do the epsilon-greedy strategy using the value epsilon t at time t. So at time t, do epsilon-greedy with epsilon equals epsilon t. And what this can do is you can balance the amount you're exploring. You can change it depending on how far into the sequence you are. So you can say at the beginning, we should explore a lot. So explore a lot at the beginning, a lot at the beginning. And that will correspond to epsilon is large for t small. T small. Epsilon t is large for t small. And explore less at the end. Explore less at the end. And that will correspond to epsilon t is small for t large. So as t gets close to capital T, then the epsilon t will get small. You'll explore less and less, and you'll exploit more and more. So this is a fantastic idea. And again, you figured out the strategy that we're actually going to analyze, which is basically this, but easier to analyze. So the problem with all these epsilon strategies is there's just so many different things that can happen, right? So every time in every round you're flipping a coin, so there's like 2 possibilities for each round. So there's 2 to the t possibilities in total, and you got to keep track of this. Especially if you vary the probabilities, it becomes quite a mess. Of course, you can do it, and it can be done. It's just a little bit more complicated. So we're actually going to study exactly this, except we are going to pick a very specific schedule, which is that we're going to make the epsilon t's 100% for the first few rounds. So you're going to be purely exploring. You never exploit in the first few rounds. And then we're going to make them all 0 for a while. You purely exploit after that. So what we're actually going to do is a very special case of the epsilon t strategy. And in general, people do this, so it's a great idea. Yeah, so you'll see it in a sec. Yeah. Anybody else have any questions or comments? Okay. And so we're going to do these in the slides. That'll help with the math, and then occasionally I'll come back to the blackboard here. But here is what we're going to do. Okay, and we're going to start with the strategy. This strategy number 0, pick an arm at random. This is the one that you guys did. I had you guys do it. Right? So you choose each arm with probability 1 over L. The number of times you pick an arm is, on average, is T over L. So the total regret is T times this thing. There's a 1 over L missing in the slide. So good thing we did it on the blackboard. I had you guys do it. Okay. That's a very nice strategy, linear in time. Here is an upgraded strategy, which is play an arm exactly once and then go greedy after that. And this, again, you can think of as an epsilon-greedy strategy, where in the first round, epsilon equals 100%. Oh, it's not exactly that. Okay, this is slightly different because I'm not picking randomly. I'm just going to play each arm exactly one time. Okay, so, but at the beginning, there's this explore phase. You're exploring. You play each round once. And then you go greedy. This is the exploit phase. Let's analyze the total regret that you get doing it this way. So, just like before, in the first L rounds, when you're exploring, I'm not even going to attempt to say what you're doing. I'm just going to bound it away. I'm going to say your regret is at most 1. So in the first L rounds, I'm just giving up. I'm saying, okay, we're just exploring here. We're trying to learn stuff. We're going to give up on trying to bound the regret. We're going to say the regret is at most 1. Okay, now we have to analyze what happens after that. So we're going to go greedy after 1 round. And after 1 round, we're going to have a sample, x1, x2, all the way up to xl, which are samples from the arms, right? And that was exactly like you guys saw when we played the game the other day. In the first round, I pressed each button 1 time, and you saw some random number, right? And the point is, the arm for the best arm, the one we're trying to find, on average will be slightly higher than the other arms. And that will hint us, when we go greedy, we'll have a slightly higher than just 1 over L chance of picking the best arm, okay? So the number of times we play each arm is the probability that the arm is the maximum out of these samples, right? So imagine you hit A, B, C, D. If it happens that option C is the best, what is the probability of that? Well, it's the probability that XC was the maximum of all the arms we saw. So the number of times you play each arm is 1 at the beginning plus T minus 1 times the probability that you chose that arm forever, that it was the best arm. Okay. And if you do the expected total regret, you will again get a linear function. Why is it a linear function? Well, there's some constant in front, and then all the other arms, again, there's some constant in front of them times t. So it's still a constant. But the thing is, this constant value hopefully is a little bit better than 1 over L. And that's because you have a slightly higher than 1 over L chance of picking the best arm, and a slightly lower than 1 over L chance of picking the crappy arms. So overall, you should do a little bit better with this strategy. We're going to soup this strategy up. Instead of trying each arm once at the beginning, we're going to try them n times. And then we're going to go greedy after that. And this is the strategy we're going to analyze in a lot of detail. Explore each arm n times, then go greedy. Okay, so in the first NL rounds, you're just exploring, I'm going to say the regret is at most 1. If n is large, we're going to use the central limit theorem. So if you explore for a large number of rounds, then not only do you know that what you got out of each arm is some random variable, but you know the average will be approximately normal with mean mu and some variance, sigma. I think there's a little picture over here. So this is maybe a flashback from your statistics classes. And you can think about this like when we were playing the game. We had option A, option B, option C, option D, and you had those averages that were showing up. And those averages, they were not exactly what was going on, right? You don't know which arm is the best. But as you try them more and more, they get closer and closer to the true average. So the error in your approximation goes like square root of n, where n is the number of times you've tried each arm. Okay. So here's a picture of what you get, right? So when you play this game, the average you see after n rounds, it's going to have some distribution that looks like this. And it's going to be centered on the true mean of the arm, but there's some width, which is like square root of n. Okay. And the more you try it, the more narrow it gets. The more sure you are that the average you see is the true average. This is all flashbacks from your stats class. Any questions or comments about this? How well do you guys remember? Some people are nodding. Maybe the people who are stunned with PTSD are quiet, but the people who are nodding are getting it? Okay. Let's keep going on. You're going to see how we use this in a calculation in 1 second. Okay. So if n is large, there's a high probability that the average we see is close to the true mean of the lake, of the arm. Okay. So, we can sort of rule out with low probability what you see is far away. Okay, and we're going to use this version of a precise version of this. This is called Hoeffding's inequality. Hoeffding being some German mathematician. So the probability that the average, that's the average you see, the empirical average, the experimental average of clicking through, and the average you see in the first n rounds, the probability that it's within c over square root of n of the true average is high. And what do I mean by it's high? I mean the probability that you're between here and here is bigger than 1 minus e to the minus c squared. So c is some number, and this probability is at least 1 minus e to the minus c squared. It's getting very high as c gets large. That's what we're going to use. And this will control us. This will say if we play n rounds and n is big enough, then we can be sure that the averages we see are close to the real thing. Okay, so we're going to make a definition. We're going to say our exploration phase, where we play for n rounds, we're going to say it succeeds with error at most c over square root of n. What could that mean? That means that every single arm is within square root of n. So for every single arm, the average that we see, the empirical average that's displayed on our screen, if that is close enough to the true average within c over square root of n for every single arm, then we say, yay, we did it. We explored successfully. That's our exploring successfully thing. Okay? And if we are, sometimes I'll just say succeeds. So later in the slides, you'll see, I'll say the exploration phase succeeds, and I will leave off the c over square root of n, but don't worry, they're still there. Okay, so we're going to explore for n rounds, and we have this notion of what it means to succeed, and by Hoeffding's inequality, we know the probability that it succeeds. The probability it succeeds is at least 1 minus L e to the minus c squared, and the probability that it fails is at most L e to the minus c squared. And that is because every individual arm, by Hoeffding's inequality, when n is some big number, the chances are that it's high probability that it will succeed. So every individual arm has at least chance 1 minus e to the minus c squared to succeed. There's L arms, so you can bound it by multiplying by L or adding the probabilities if you want. Okay, so if we cook this up right, we're going to have it so that we succeed with high probability. Okay, here is the proposition. Actually, before I do the proposition, let's go back now. Any questions up until now? I think this is the hard probability has come at you now. What does it mean to succeed? What does it mean to fail? It's all on there, but please let me know. Questions? Okay. So now here is the whole shebang. Why are we doing this? Why do we care that our exploration succeeds or fails? Why would we care? Here is the proposition. If we succeeded, then when we go to exploit, we achieve low regret. And this is the thing. I don't know if you remember when I was doing this very simple hand-wavy approximation, I said a regret of 0. And I was like, we hope that we've explored enough that we get a regret of 0 once we start exploiting. And what we're doing in the slides, we have made this precise. And it's not 0. We cannot get a regret of 0, but I can make sure the regret is at most, what was it? It was 2c over square root of n. So if your exploration phase went well and you succeeded, then you get small regret in the greedy phase. Let's prove why this is true. This is not so hard to see. So that's the proposition. Okay, here's the proof. Let's go to the blackboard for the proof. Okay, so we can do it in a little more detail and a little more slowly. Okay, so we're analyzing the algorithm, which is explore for n rounds per arm. Explore for n rounds per arm, NL rounds total. And then we're going to exploit for the rest. T minus NL rounds. Okay. And we have said exploration succeeds if all arms are within c over square root of n of true mean. So the average of arm A up to time n, after we've tried it n times, minus the true average is less than c over square root of n and is bigger than minus c over square root of n. So this is what it means to succeed. And the proposition we're proving, the proposition says, if we succeed, then during greedy phase, get no worse than 2c over square root of n regret per round. Okay, that's the proposition. And I'm going to give you the picture proof first. So this is going to be the picture proof. The real proof is in the slides, but here is the picture proof. And what I'm going to do is I'm going to draw a number line for each arm. So here's arm A equals 1, here is the arm A equals 2, and here is the arm A equals 3, here is the arm A equals 4. Okay. And so on. I guess let's go with 4, because that's what we had in our example. And these are little number lines that I've drawn over here. So you should think of these as number lines that are vertically stacked. So you can see which number is better and worse. And each arm has a true mean that is unknown to us, right? So inside the computer knows the true mean. I shouldn't say the computer. Nature knows the true number of fish that you will catch at the lake on average, right? That's the mean of each thing. So let's try those in. So this is mu1, this is mu2, this is mu3, and this is mu4, all the way down here. So you can see, if we knew this, then we would be done, right? We know, just by looking at this, the true means that lake number 1 is the best lake. Of course, in real life, we don't get to see this, right? So this is some unknown fact about reality that we don't know. What we do know is the averages that we have seen so far, right? During our explore phase, we tried the arms, and we got some average. So maybe for lake number 1, we got this average. This is the average of lake number 1 in our n rounds of exploration. And maybe we got some average over here, the average of round 2 after n rounds of exploration. And the average of lake 3 of n rounds of exploration. And here's the average of lake 4 of n rounds of exploration. So the purple things, we don't get to see them in reality. We only get to observe what we saw during our explore phase, which are the experimental averages. Okay. And then in the greedy phase, we play the arm that has the highest average that we've seen, right? So in this example, the way I've set it up, which arm would we play? During our greedy phase, we would say, which one has the highest average? Well, we don't get to see the purples. We only get to see the averages we computed. It's arm number 2. So let's play arm number 2, right? So in the greedy phase, we would play, in this example, would play arm number 2 during greedy phase. Okay. So we would get some regret, right? We would get some regret because arm number 2 is not the best arm to play. At the end of the game, we're going to kick ourselves. We're going to go, oh, we should have played arm number 1 the whole time, right? We got it wrong. But how much regret could we possibly get? And the reason it is bounded is because we know that the average, this average, cannot be too far from mu2. And this average cannot be too far from mu1. So this one is not too big, and that one is not too big. Why are they not too big? Because we are answering the question, what happens when the exploration succeeds? And when the exploration succeeds, the distance between these two numbers is less than c over square root of n. So this one is less than c over square root of n. And this one is definitely less than c over square root of n in distance as well. I'm going to write this as the average minus mu2. And so this one I'm going to say is less than, in the right sense, less than negative c over square root of n, right? So you sort of like, you could get unlucky and underestimate the best arm, but no more than c over square root of n. And you could get unlucky and overestimate a suboptimal arm, but no more than c over square root of n. So what is the total amount of regret you could pick up? Well, like the worst case scenario is that we overestimated by c over square root of n, and the true value was an underestimate by c over square root of n. In that case, the total we would be off by is 2c over square root of n. So the distance between mu1 and mu2, the total regret can't be more. So mu best average minus mu actual best is going to be less than 2c over square root of n. That's the regret of the arm we pick. So that's the picture proof. If the picture proof makes sense, then the algebra is like a snap. It's like one line. But if you don't understand what's going on, then the algebra is just like some crazy thing that came out of nowhere. So tell me, what do you guys think? Is the picture proof okay? Any questions? Okay, let's go to the algebra. Let's go to the algebra. So here's the proof with the algebra. In one line, right? The greedy arm has a gap of no more. So you take mu star is the best thing, minus mu a is the one we're picking. And you bound mu star can be no more than the average plus c over square root of n, and mu a can be no less than the average minus c over square root of n. And then you add these up and you get 2 over c over square root of n. Very nice. This is like the algebra version of what we just did in one line. If you understand the picture proof, then this one is a breeze. Okay, great. So we have this whole thing set up. We have this notion of exploring and then exploiting. We know that as long as we succeed, then we get no more than some amount of regret. And now we can add everything up. So we're going to explore each arm n times, and then go greedy. How much regret do we have? We have 2 sources of regret. We have regret from the explore phase and regret from the greedy phase, and we're going to add them together. And the regret from the greedy phase can be divided into 2 parts. There's the regret when we succeed, and we know that's low. But sometimes we will fail. Our exploration will not work, and we'll get unlucky, and we won't have an accurate estimate. And in that case, I'm going to say the explore fails, and I'm going to divide the total regret from the greedy phase into 2. Explore succeeds and explore fails. And you have to, when you're doing the expected value, you multiply them by their respective probabilities. And now we have an answer, which is we can add all these 3 things up. The regret from the explore phase is n times L. I'm just saying the regret is less than 1 in each round. There's NL rounds. Great, NL. When the explorer succeeds, that's this term, then there's no more than 2c over square root of n regret per round. That's what we just did. You play t minus NL rounds. Very nice. When the explorer fails, I'm going to give up. And again, you get a lot of regret in this situation. When the explorer fails, you really get a lot of regret. But we know that the probability is small. And the probability is less than L times e to the minus c squared. So at the end of the day, we've bounded the regret by NL plus TL e to the minus c squared plus 2c over square root of n t. Okay. This is all a very, so far everything is perfectly rigorous and mathematically correct. We have done basically a more rigorous version of what I did over here, right? This kind of idea of having an explore phase and then hoping that the regret is small over here. There's, again, 3 sources of regret. The regret at the beginning, the regret when exploring goes well, and the sort of like extra stuff you get. And in this situation, it's the same thing. You have these 3 things. Okay. Any questions about how I came to this calculation of the expected total regret of exploring for n steps and then doing this kind of thing? Then going afterwards? Yeah.
For the c squared of n, is it like the sampling mean distribution standard error
So
type thing?
yes, exactly. So the reason we had this e to the minus c squared, technically it's by Hoeffding's inequality, but it really is because we can approximate the average by this normal distribution, and we said exploring succeeds means you're within negative c over square root of n to plus c over square root of n. And so what is the probability of the exploring failing? It's the tail distributions, which are like e to the minus c squared. So it's like an inequality version of the sampling distribution being close to the true distribution. That's exactly right. Very good question. Anyone else? Okay, so now we have this whole family of strategies because we can do this for any value of n, right? You can choose the value of n that you want. You can also choose the value of c that you want, right? You can say, I really want to succeed with like a really high probability, or you can say like, I'm okay with succeeding only 50% of the time. So you get to choose the value of c, and you get to choose the value of n. And when you choose the value of c and the value of n, you get some answer, some actual answer. And so what we're going to do next is we're going to optimize and find the best value of c and n. If you've taken like an optimization class, or even just like a good multivariable calculus class, you know how to optimize. How do you optimize? Well, you take the derivative and set it to 0. When you take the derivative and set it to 0, you'll see actually another phenomenon that comes up a lot. You have 3 terms, and if you want to make this whole thing as small as it can be, you want all 3 terms to be approximately the same size. If one of the terms is much bigger than the other ones, then you could bring down the whole thing by making the other one a bit bigger. This is a little bit like in calculus class when it's like, oh, there's a rectangle, and please find the dimensions of the rectangle to maximize the area. And then it always turns out that it's a square, right? So you try to make all of the terms sort of equal in size, that's the optimum. Same thing, they do it with a cylinder, all of these things. It's a lesson that comes up over and over again. You want all 3 things to be about the same size. You can prove it rigorously with derivatives, but I'm just going to take that as a starting point. So let's optimize. So find the n and the c that minimize the bound. Let's do it. So this is the equipartition principle. Let's make them all approximately the same size. And so NL should be approximately this much, should be approximately that much. I'm going to go over this slightly quickly because I don't want to spend too much time just optimizing some equation here. So when n is t to the 2/3 and c is the square root of 1 over 3 log t, you might say, why do you have a square root of a log? Well, it comes with an e to the minus c squared. E to the minus c squared exactly undoes square root of log. So when you set this up so that c is the square root of 1 over 3 log t, then e to the minus c squared is exactly something like t to the 1/3, or t to the minus 1/3. So if you plug in these things, then they are all about the same. So then they are all about the same. And when you do that, you get a total regret that is less than t to the 2/3, which is amazing news for us. Because, if you remember, we were trying very hard to beat the linear regret. And we have now found a strategy that gets regret of size t to the 2/3. And that is sublinear. This means, as you play more and more rounds, the amount of regret still grows over time, but it grows less than the total number of rounds you play. If you play 1 billion rounds, then 1 billion to the power 2/3 is only 1 million. So you play 1 billion rounds, you only get 1 million regret. That's amazing. That's a 1 over 1,000 sort of regret reduction from doing the linear way. And all you have to do is you can interpret what this means. N is t to the 2/3. You explore for the first 1 million rounds, and then you go greedy after that. I think I have some picture about this. Okay, actually, let's do this quick example. So let's write this one down. I think it's worth doing. So get that n equals t to the 2/3 achieves regret. Expected total regret equals also t to the 2/3. And so the example, if t equals 1 billion, also known as 10 to the 9, then n equals 10 to the 9 to the power 2/3 equals 1 million. So you explore for 1 million rounds, and then you go greedy after that. And the total regret you have will also be about 1 million. The total regret is on the order of 1 million. Very nice. So you can get a lot lower regret than just accepting that you're going to get linear int regret. This is some simple example with 1 billion and 1 million to give you an idea of the numbers and what they mean if you're not used to thinking about these exponents. Okay, any questions about this example or the setup here? Yeah.
Will these slides be posted?
Yeah, I can post them.
Oh,
Yeah.
thank you.
Okay. So, in this strategy, we explored for n rounds. We tried every single arm n times. Just like sit there, try the first one n times, sit there, try the second one n times, and so on. Can anyone think of a simple way to improve this algorithm? So this would be the version of, in the game we played, before we did anything else, before I let you vote, we would just sit there and try every arm A some number of times, sit there and try arm B some number of times, sit there and try arm C some number of times, sit there and try arm D some number of times. And then I let you vote. Can you think of a way to improve it? Yeah.
If there's no, like, how we did in value iteration, if there's no change in the values of average, we can just stop.
Yeah, that's right. So you can, and it's not only that, if they're not changing, then you can stop. That's great. You're like, okay, I'm pretty sure I got it. But remember, we don't need to estimate them accurately. We only want to make sure we don't accidentally select the worst arm, right? Like we want to make sure we pick the best one during the greedy phase. So you can stop even sooner than what you're saying. Yeah.
Can we just keep on going until the errors don't overlap anymore?
So this is a great idea. We don't actually know the errors in real life, right? Because we don't know the true value.
Expected errors.
So I'll tell you what we did. Let's go back to the picture. So we know just the averages. And these averages, as we try them, they bounce up and down, right? You guys saw that when we were playing the game. So you try it one time at some number, and then as you try it more, it goes up and down and up and down. The more you try it, the less it moves, because once you've tried it 100 times, the 101st time doesn't have much influence, right? So the averages, sort of as you're trying it, are bouncing up and down and up and down. And we said, let's try it enough times so that we're pretty sure that each one is accurate. That's what we did so far. We said we're going to try it a lot of times, 1,000,000 times each, so that we're very sure they're all very accurate. And then we're like, once they're accurate, now we can pick the best one. That's what we did so far. Can you think of something better to do that would save on the exploring? Maybe there's some that we need to explore not as much, that we could do less. Yeah.
When the average stops moving, or moves very, very slightly, then you can stop exploring it, just assuming it's not going to move anymore.
Yeah. So this is one thing. If you have some other reason to think it's accurate, then you can stop. But I think there's something even better we can do, which is we're being too demanding by saying we need all the arms to be accurate. That's what I think the issue is. So you're right that if for some reason we know this one is accurate, we can stop there. But I'm saying even if we know it's inaccurate, sometimes we can still stop early and not waste our time exploring, even though we're inaccurate. Yeah.
If our range is like in a certain area that doesn't overlap the other ranges.
That's right. So remember, we only care about finding the best arm. Like, if we're pretty sure it's between this one and this one being the best, then let's try those ones a lot and see which one really is the best. This one's all the way down here. This one sucks. We're not going to pick this one. Like, why would we waste our time getting a really accurate estimate for something that we then don't use? And so the idea is, let's only be accurate about the top contenders, right? Let's not waste our time on the people who are doing badly. Those people aren't even in the running for what we're going to pick. So when the sort of range of what this one could possibly be is not even close to the range of what our top value is, then there's no reason to explore this one. So this idea is called adaptive exploration. Adaptive exploration. Okay. So spend less time exploring the disappointing arms and more time on the promising arms. So instead of trying each arm equally, let's try them, and we'll try the ones that are doing well, we'll try those more. We'll try the ones that are doing badly, we'll try those less. And by doing this, we're going to save some time in our exploring phase. And you're going to see it leads to an actual big increase in what we can get. So this is called the upper confidence bound algorithm, and this is what the AI was doing in the game we played yesterday with the lakes. The upper confidence bound algorithm. Here's how it works. In the first L rounds, we play each arm once. So we're going to start with one try for each arm. Then we're going to compute something called the upper confidence bound for each arm. What is the upper confidence bound for each arm? It's the average plus 1 over square root of NA times some constant. And so what this is going to do is the arms that we have not tried many times, they get a big boost. So you can think of the average as getting a boost here depending on 1 over the square root of the number of times we've tried it. I'm going to draw this as a picture just for you guys to see. So I'm going to redraw this picture with the number lines. I think this is the right way to think about it. So here's arm 1, arm 1, arm 2, arm 3, and arm 4. And we have the average for each one. Let me draw the same color as before, keep things consistent. We have our average, the average 4 of N4, the average 3 of N3, the average 2 of N2, and the average 1 of N1. So these are the averages. If you were playing the greedy algorithm, you'd say, I'm going to pick the one with the best average. In the upper confidence bound algorithm, you add on a boost to each of these. And the boost you add depends on 1 over the square root of the number of times. So you're going to add a boost on. And that boost is going to boost it up. This is the UCB of 1. UCB stands for upper confidence bound. And it's the average plus 1 over the square root of N1 times some constancy. And so each of them is going to get a little bit of a boost. UCB2, you get plus 1 over square root of N2. UCB3, maybe, let's pretend this one has a huge boost. UCB3, 1 over square root of N3. And this one has a small boost. UCB4 is plus 1 over the square root of N4. Okay, and let's also check our battery levels. Okay, we should be okay. So each of them is getting a boost. Now you'll notice the sizes of the boost they're different, right? Some of them get a big boost, some of them get a small boost. Which ones get a big boost? In my example, I gave this guy a big boost. This guy has a super small average, but he got a huge boost. Why did he get a big boost? It's because N3 must be very small. If N3 is really small, that means we haven't tried this arm very much, so we get a big boost to this arm. And this is representing the fact that, look, you haven't tried arm number 3 many times. And so even though it has a low average, it could be that we just got unlucky, right? Like, we're quite unsure about the average of arm 3. And in fact, the reason it's called upper confidence bound is if you were going to draw a confidence interval for the true average, the mu3, that unknown purple mu3, you would be 95% sure that it's somewhere in this region. So this is the confidence bound for mu3, the true average, right? So for all we know, the true average could be all the way up there, right? Maybe it's all the way up there. And so because we have a very wide confidence bound, that means we have more uncertainty about what the true average is. And so we should spend our exploring trying this arm to get a better thing. And so what the UCB algorithm does is it looks at the average plus this boost. It looks at the top of the confidence bound, the upper confidence bound, and it says, let's try the arm that has the largest upper confidence bound. So in this example, even though mu3 has quite a small average, the upper confidence bound algorithm would choose to play arm 3, and in that way, as you play arm 3 over and over again, the bound will shrink. And eventually it will shrink, and then maybe we'll start trying those two again, right? But actually, one thing that can happen is as we play it more and more, maybe we'll realize, oh, geez, we were wrong. The average of arm 3 is actually quite good, and it goes up, right? And then we'll know that arm 3 is the best arm. So by doing this, we're sort of balancing how good the arm is with our knowledge of the arm. And we're playing the arms where we either have low information or they're quite terrible. So we're kind of balancing both automatically. So that's the idea. Let's go back to the thing. Okay, so that's the UCD. You boost it so that this is the upper confidence bound. And we play the arm with the highest UCB. That's what the computer did. It calculates the UCB and plays the arm with the highest UCB. And you just do this forever. So it's a very simple algorithm. The exploring and exploiting are mixed into one. Very early on, you will try arms that have very low NAs, right? That'll be like exploring, because you'll have these really wide confidence bounds on the arms that haven't been played much. And as later in the game, the confidence bounds will shrink, and this will kind of go to 0, and you'll basically be doing greedy, choosing the highest average. Okay. This algorithm has a bound, not of t to the 2/3, a million regret in a billion rounds, but t to the 1/2. What is the square root of a billion? I guess it's 10 to the 4.5. So like a regret of 20,000. So in a billion rounds, you only get a regret of 20,000. To me, this is like an absolute miracle that you can get a regret this low. And this algorithm works really simply. You got compute one number and take the maximum. To me, this algorithm is like some kind of like genius level, amazing like miracle of this field. Okay, the UCB algorithm. Here is how you would prove it. I won't give you the full details, but basically what's going to happen, with high probability, the UCB algorithm plays suboptimal arms not too many times. So if an arm is actually suboptimal, the UCB algorithm can only try it until the confidence bound narrows. And once the confidence bound narrows enough, then you'll know that one is worse, and you'll play a better arm. So it won't play them very many times. And in fact, the bigger the delta is, the less times you'll play it. If you have an arm with a huge gap, then as the confidence bound shrinks, you'll play that arm less. So you can't play it more, on average, than 1 over the gap size squared. So it kind of spends a lot of time playing the good arms and very few rounds playing the bad arms. Okay, and you can add this up to get this kind of regret. This is a different kind of bound as before. Okay, I want to tell you the application of this, which is this thing is the basis of how the AlphaGo 0 algorithm works. So it uses upper confidence bounds to compute which chess moves has it thought about a lot. And it says, I'm going to think about the chess moves that either I haven't played many times and haven't thought about a lot, or are very promising. And I'm going to balance how promising it is with how many times I played it by computing the upper confidence bound. And so this is how the AI works. It calculates this UCB. It uses a neural network to sort of like balance these two things. And that's partially how it works. And it does this kind of like loop. Let me skip over here. It does a loop over here that you've seen before. You have some neural network function that is kind of guessing how promising things are. And then it updates that by playing a lot of games to find a better version. And then this like nice loop of play lots of games using some function. Use the played games to improve your function. We've seen this before many times. But it uses the upper confidence bound algorithm, which achieves this like miracle regret, if you ask me. Okay. Any questions or comments about any of this stuff? I know I kind of went over this last thing quickly, but hopefully at least the definition of the algorithm makes sense. It is tricky to analyze. So the one you saw was like the easiest thing we can analyze that achieves sublinear regret. This one achieves square root regret, but it's harder to analyze. Questions? Okay. So let me make a quick announcement. So next week I will be gone. I'm going to a conference, but we're going to have a guest lecturer from Waterloo who is an expert on bandits come and tell you some stuff about bandits. So we're going to learn more. I think he's going to talk about adversarial bandits. So in adversarial bandits, an adversary is trying to like screw you up. You'll see what they are. And you can get a whole different kind of thing. You're going to see more analysis of algorithms like this. And yeah, they apply in real life. I think they're really cool. And it's a really cool place where you can do like theoretical work on real life computer science stuff. So that'll be next week. I will post some information about the final project. I am thinking to let you guys work in pairs for the final project, which I think will be more fun for you than just slaving away on your own and having computer bugs. Now you can show your computer bugs to the person next to you and get some help. If you feel strongly about that, you can let me know, but that's probably going to happen. The code for the final project is already posted, so you can start to think about it and come up with your strategies, but it's going to be essentially, I'm going to let you do whatever you want at this Casino Easy 21. So start thinking of ideas now. Lab 3 will be posted soon, hopefully. And yeah, that'll be it. So I'll see you guys not next week because I won't be here, but please do come anyway because there will be a guest lecture, and I'll see you the week after. Yeah, question over here.
So you said lab 3 will be posted next week, you'll be gone next week.
That's right.
Is it on the same day, the 14th, or no?
No, it's due a week later. So it's not due next week, it's due the week after.
Right, it'll still be open on the 14th.
No, sorry, the day we do it in class is not the 14th, it'll be the 21st. Which-
We're not doing it, okay.
So there'll be an in-class day on Thursday, but the Thursday I'm back. So not a week from today, but 2 weeks from today will be the lab day in class. Yeah. Yeah.
Do we have guest lectures both Tuesday, Thursday?
Both Tuesday and Thursday. Yeah, that's the plan. Oh, but do keep an eye on the announcements in case it changes. That is the plan right now, but it might change. Yeah. Thank you for remembering. Okay.